All right, so to finish up chapter 1, we want to talk a little bit about temperature, heat, and energy, and then the concept of density. So energy is the capacity to do work or supply heat. And temperature then is the measure of the amount of heat energy that's in an object. And in the United States, this is commonly reported in the units Fahrenheit. In the metric system, Celsius is used as the common unit. And then the SI unit for temperature is the Kelvin, or K. Note that we only say Kelvin, not degrees Kelvin, when we're talking about Kelvin. So the Kelvin and the Celsius degree are the same size. So a change in temperature of 1 degree Celsius is equivalent to a change in 1 degree Kelvin. So the Celsius scale assigns a value of 0 as the freezing point of water. So 0 degrees is the freezing point of water, and then 100 degrees Celsius on the Celsius scale is the boiling point of water. So the Celsius scale is really designed around water. The Kelvin scale, on the other hand, is designed on absolute 0. So this is the coldest possible temperature, and at this temperature all of the molecules stop moving. So it's really designed or based around the movement of molecules. So we'll see at higher temperatures that are above absolute 0, you start having the movement of different elements or molecules on the Earth. So at temperatures above absolute 0, you start having the movement of molecules. So if we equate Kelvin scale to the Celsius scale, we'll see that absolute 0, or 0 Kelvin, is equivalent to negative 273.15 degrees Celsius. So this serves as our conversion factor. So we can say 0 degrees Kelvin equals negative 273.15 degrees Celsius, or that 273.15 Kelvin equals 0 degrees Celsius. And so this is our conversion factor that we utilize when we're converting between Celsius and Kelvin. So essentially, if we're converting Celsius degrees into Kelvin, then we just add 273.15 Kelvin to that number, and we will have our temperature in Kelvin. So the Fahrenheit scale was actually a little bit more arbitrary. It was based on the lowest freezing temperature that could be obtained by adding salt to water and making a briny solution. So at this point, 0 degrees Fahrenheit was listed as the freezing point of the brine solution. And so the actual freezing point of pure water then is at 32 degrees Fahrenheit, and the boiling point of the water, of pure water, is at 212 degrees Fahrenheit. So the Fahrenheit scale is a little bit more arbitrary, and it doesn't have a one-to-one conversion to the Celsius or the Kelvin scales. So a change in temperature then of 1 degree Celsius is equivalent to a change in 1.8 degree Fahrenheit. So it takes 180 degrees Fahrenheit to cover the same range that's encompassed by 100 degrees Celsius. So you have to use this conversion factor when converting between Fahrenheit and Celsius. And then you have to add 32 degrees to that number as well. So these are the temperature conversions. You will be given these on the exam as well, at least one set. So you might have to rearrange your equation to get one or the other. But we know our Kelvin scale is equal to our degrees Celsius plus 273.15. So this is a very easy conversion. You just have to add those degrees. And that's because the Kelvin scale and the Celsius scale, each degree is comparable to one another. If you move 1 degree up in Celsius, you also move 1 degree up in Kelvin. The Fahrenheit and the Celsius scale, however, are a little bit different, and you have to use that 1.8 degree conversion to get to the correct conversion in Celsius or Kelvin. If you have Celsius degrees, to figure out how many Fahrenheit degrees that you're going to have, you would have to use this equation here. So this is what you would be solving for. So it would be 9 degrees Fahrenheit over 5 degrees Celsius times the Celsius degrees that you're given. So if it's 21 degrees Celsius outside, you could convert that to Fahrenheit. And then you have to add 32 degrees Fahrenheit at the end. So you do this calculation first, and then you figure out your degrees, and then you would convert that into Fahrenheit. And we'll do a worked example of this here in a few minutes. And then if you're calculating degrees Celsius from degrees Fahrenheit, you have to do the opposite of this calculation. So first you have to subtract off 32 degrees, and then you have to multiply this by 5 degrees Celsius over 9 degrees Fahrenheit to get the correct conversion. So there's been some cool developments in measuring temperatures, and this utilizes some temperature-sensitive materials. So there's thermochromic materials, and maybe you've seen this, especially if you have a fish tank or a reptile cage. They often use thermochromatic materials that change color as the temperature changes to indicate the temperature that you have in your tank. And so these liquid crystals then are incorporated into either plastics or paints, and they can be used to monitor the temperature changes. So like in your fish tank, your temperature gauge might be in the blue range, and you want to keep it in that blue range. If it gets up into the red range, then the water is heated up too much. So hospitals and other medical facilities now routinely use these thermochromic materials as well in these temperature strips that will help to change color and indicate body temperature. So in the future, we may also see things like road signs that change color to warn of icy road conditions. That would be very interesting to have. You could see very easily, oh, the sign's blue now, so it's very cold outside and might be slippery. So this is just representation of the Fahrenheit, Celsius, and Kelvin scales, just showing you the base conversions between the two. So you can use this to estimate your temperatures from. This is kind of a nice guide scale, but if you're calculating and you want very exact answers, you need to use the conversions that we gave, the mathematical conversions that we gave on the last table. So changes in temperature represent that heat is either being absorbed or heat is being released from a reaction. And so the movement of heat is going to indicate when energy is either being expended or when it is being gained by a system. So if energy is required for a reaction, the surrounding temperature is going to drop as the reaction actually takes the heat from the environment. But sometimes energy is released from a reaction, and it'll be released in the form of heat, and it will increase the surrounding temperature. So to measure energy, energy is going to be represented by our SI units, and the SI units are a joule for energy, and then the metric unit is the calorie. And so the calorie is still widely used, and we use that to evaluate the energy that's stored in our food molecules. So you'll commonly see calories at the supermarket. And the calories that we actually see at the supermarket are not real calories. They're actually kilocalories. So they're 1,000 calories is equal to 1 big calorie. So we don't like to put the kilocalorie on all of our food labels because it's big and it's a bulky word to say. So they just use the large calorie on our food molecules. So the food companies have dropped kilo and just call it the big C, or the big calorie. So a food calorie by nutritionalists equals 1,000 calories by a scientist that would be using or measuring calories within the lab. So do you guys know how many calories a gram of protein has? That's correct. It's got 4 calories per gram. So carbohydrates also has 4 calories per gram. And then lipids or fats have more calories per gram. They're richer in energy, and that's why we don't need to eat as much of the fat materials, because they have higher energy and you can gain weight faster if you eat fatty foods. They have 9 calories per gram. Interestingly, ethanol or grain alcohol, so beer and wine and things like that, ethanol is going to have 7 calories per gram. So you have to be careful if you drink a lot too. There's a lot of calories in beer. So the definition of a calorie is listed here. 1 calorie is going to raise the temperature of 1 gram of water by 1 degree Celsius. So that's the energy that's required to increase the temperature of the water. So 1 calorie can raise the temperature of 1 gram of iron by 10 degrees Celsius. So the amount of heat that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius is called its specific heat. So each specific compound or material is going to have its own specific heat. We'll see that water is actually very special because water can absorb a lot of heat without changing temperature. And you can see that that's evident here. If our definition of our calorie is that it raises the temperature of 1 gram of water by 1 degree Celsius, that same amount of energy can raise the temperature of 1 gram of iron, the same amount, by 10 degrees Celsius. So you can see there's a huge increase in the temperature in iron where there's hardly any change in the water molecules. And so this is a unique property of water, and it actually is an important feature of water because it really helps to regulate the temperature on the Earth. So it can absorb a lot of heat input from the sun without changing the overall global temperature on the Earth. So water acts as a huge temperature sink. So if we know the mass and the specific heat of a substance, it makes it possible to help us calculate how much heat has to be added or removed to accomplish a given temperature change. So you can see that some of the specific heats of different compounds, you can see the specific heat of iron is very low. It's only a tenth. So 0.1 calories is enough to change 1 gram of iron by 1 degree Celsius. You can see, again, the specific heat of water is very high compared to most other substances. It can absorb a tremendous amount of heat before it actually changes its temperature. And then the conversion to joules is written here. So 1 calorie is typically 4.18 joules. So we can convert in between calories and joules as well. All right, so let's do some temperature conversions. So if we start off and I say we have, I don't know, the room is at 24 degrees Celsius. What is that temperature in Fahrenheit? So I've given you this information and I want to know what degrees Fahrenheit we're going to get from that number. So the first thing that you should know is the Fahrenheit scale is a larger scale than Celsius, and so the number that you should get in Fahrenheit is always going to be larger. So this is our ballpark figure. Fahrenheit should be larger, Celsius degrees are smaller. So our conversion, if we want to get Fahrenheit, is degrees Fahrenheit are going to equal 9 degrees Fahrenheit over 5 degrees Celsius times our degrees Celsius. This is going to be plus 32 degrees Fahrenheit. So that is our conversion factor. So if we substitute in our value for Celsius degrees here, we can put that into our equation. We know we've got 24 degrees, that's going to come down here. So we put in 24 degrees Celsius, and if we calculate that out, that should give us our degrees Fahrenheit. Alright, so when we calculate that, we find that we get 75.2 degrees Fahrenheit. Now if we look at our answer, we see that in our original question we only have 2 significant figures. So that's what we need to represent our answer in as well. So we need to do some rounding. Using our rounding rules, this position here is less than 4, so we're going to round down. And we would say our final answer is 75 degrees Fahrenheit. So this answer is larger than our initial value, and so this would be equivalent to our ballpark figure. So 75 degrees Fahrenheit equals 24 degrees Celsius. So if we had, so this would be nice comfortable temperature if you wanted room temperature. So if we had 108 degrees Fahrenheit, what is that value in Celsius degrees? Let's do the reverse type of equation. So our conversion equation then, to get back to degrees Fahrenheit, or to get back to degrees Celsius from Fahrenheit, our degrees Celsius are going to equal 5 degrees Celsius over 9 degrees Fahrenheit times the degrees Fahrenheit that we're given minus 32 degrees Fahrenheit. So if we're given 108 degrees Fahrenheit, we can put that into our equation down here, 108 degrees Fahrenheit, and we can use this to calculate the degrees Celsius that we should get from this. So 108 degrees Fahrenheit minus 32 is 76. We multiply that by 5, divide it by 9, and we end up getting our degrees Celsius as 42.222 degrees Celsius. We can see in our original question we have 3 significant figures, and so we need to reduce this to 3 significant figures. We can see at this position here, that's a 2, so that's less than 4, so we're going to round down. So our final answer should be 42.2 degrees Celsius. This is equivalent to 108 degrees Fahrenheit. We also can do our check again. We know that the Celsius degrees should be smaller, our Fahrenheit degrees are larger, and this is equivalent in our equation here, and so we have the correct answer. So we'll do one more conversion for temperature, and we'll go from the Celsius to the Kelvin scale. So if I have 27 degrees Celsius, and I want to know what is this in the Kelvin scale. So Kelvin, we know that Kelvin are going to equal our degrees Celsius plus 273.15. And so for converting into Kelvin, it's very easy. We're just going to move our degrees that were given in Celsius. So we put in 27 into that position, add it to 273.15, and see what we get out. So our answer in Kelvin is 300.15 Kelvin. And what do we know about our answer? We should have 2 significant figures in our answer. So we are going to need to do a little bit of rounding. So we can round at this position back up. This is below 4. Even if we round up at this position to get 0.2, that's still going to be below 4. We round again. That's going to round down, and so we're going to be left with 300 Kelvin as our final answer. Remember, we can't tell by this number whether these zeros are significant. In this case, the 3 and the 0 are significant, and the third position here is not significant in this case. If we wanted to express this as being significant, we could put it into scientific notation, and we could say 3.0 times 10, we would have to move this back 2 decimal places to the 2 Kelvin, and this would indicate very nicely that these 2 positions are significant and that the third position in our normal or standard representation of this number is not significant. So these represent some conversions between different units of temperature.